In this video, we are talking about the basic idea behind differential calculus, and that is finding the slope of a curve at one specific point. Differential calculus talks all about the rates of change, and we are used to finding the rates of change by using our slope equation over here. But calculus talks about the rates of change at an instant. So we're going to look at what is the rate of change at this one point. Okay, so we're going to use a tangent line that is touching our curve. Our curve here is our f of x equals x squared. It's a function x squared. So we're going to look to see what is the slope at that one point. So we draw this tangent line. This tangent line touches the curve at one point, that one specific point. And it's perpendicular to the curve at that point as well. So if we wanted to find the slope of this, we go again over to our slope formula and plug in our 2 points, and we're good to go. However, we do not have a second point, so we can't really do the slope equation for this tangent line. So what we're going to do is we'll draw a secant line. A secant line is a line that cuts through a curve at more than one point. Now with a secant line, we can see that the change of these two lines are very different. But let's look at the slope of the secant line because I want to show you where a couple things come from. So if we were to find the slope of this secant line, we're looking at our, let's see, we've got our first point is 1, 1, and our second point, well, we're saying down here that x is going to be 3, so we've got f of 3 is going to equal 3 squared, so obviously f of 3 is going to be 9, so we have our second point of 3, 9. Now you probably did all that in your head anyway, but like I said, I want to show you where some of this stuff comes from. So we're going to find our slope. So our slope is going to be 9 minus 1 over 3 minus 2, which is 8 over, well, not 3 minus 2, 3 minus 1, which is 8 over 2, which is a slope of 4. Okay, so we have the slope of our secant line at 4. And again, these two things are very different, the slopes between the two. But what we can see is this 2 right here is talking about the change in difference, or the change in distance from our first point, 1, 1, to our second point, or to the x value of our second point at least, which is 3. So that talks about the change in x. Now, we might use the term change in x with delta x. I'm going to use h. This is another method that you can do this, is either one of these two things, but they both are saying that our change is 2. So our change from our first x, for the x value of our first point, to the x value of our second point is 2. Now what we need to do is we need to find a way to get that secant line so close to the point 1, 1 where it will be practically 0 but not 0. Because what happens if it is 0? Well, let's get rid of this and let's take a look to see what happens when we get rid of this. Alright, so as we move our slope of our secant line closer and closer, we can see we're getting a better approximation of that tangent line slope until we get all the way to the point 1, 1, where now you can see our h up here on the slider is 0. So the change in the values is 0. Well, we don't want it to be 0 because when that happens, we're down to 1 point again. We can't find that slope. So we're going to move it up just a very, very little bit, 0.01. But if you look closely, you can see both blue and red on here because the secant line is not actually at the tangent line. There's still a difference in slope. So how do we get both of these things, or how do we get this tangent line when we need a second point? Well, this is where our calculus comes in. Alright, so let's look at a clean sheet and work some of this out. Okay, I'm going to start by looking at our basic slope formula. So we already said that our slope is y2 minus y1 over x2 minus x1. And we saw in the previous, with the previous images, with the graphs, that these things came from our values of f of x and whatever x was. So actually, let's do it this way. It's actually our values come from whatever our x is and our f of x. So there was our first point, right? Our first point was 1, and then our second, and the y value for that was f of 1, which was also 1. So we get the point 1, 1. Right? And for our second point, just to kind of to drive this home, we said our x was going to be 3. So our y value is going to be f of 3. And we know that we were looking at the function. What was our function? Our function was x squared. So we're looking at this function. So when we had our 3 and then our f of 3, we come up with 3 and f of 3, which is 3 squared, 9. Okay, so yes, we know all that. That's great. What's that do for us? Well, what we're going to do is we are going to look at the change of these things and how this works into our equation. So we saw before for this function, or for this secant line that we first started with, that our slope was going to be 9 minus 1 over 3 minus 1, which we saw was 8 over 2, which ended up being ultimately 4. And we said that this value, this 2, is our h. That's the change in x, the change in distance in x. So when we're looking at our slope formula now, we can say that we are looking at 2 points. We're looking at x and f of x, whoops, there we go, f and f of x, and then we're looking at our other value is x plus h, so plus the distance that we moved, and then our second value is going to be f of x plus h. All right, so let's just look at this again. So plugging our 1 and 3 back in here, I really want to drive home this point. So our first value was 1. We were adding our h value, which was 2. And then we were taking that, and we were taking our f of 1 plus 2. This was for our secant line, remember. So we ended up with, we ended up with 3 for our x, and f of 1 plus 2 is 3, which was the 3 squared, and that was 9. Okay, so great, yeah, awesome. Why do we need all this? Because as we rewrite our slope formula, we now have our second point is our x plus h. That's our second x value. Our first x value was just x. Our second y value is f of x plus h. Our first y value is f of x. Okay, so now here is a new way that we can write our slope formula. And we're talking about this in terms of h, which means how far are we moving from our first point. Okay, so that h, and if you noticed, we wanted that distance to be as small as possible, but not actually reach 0, which is the basic idea of our limits. So we want to find the limit as h approaches 0, that there's as small as change as possible for the slope, for f of x plus h minus f of x over x plus h minus x. And what this is going to give us is our slope of the tangent line. The slope of the tangent line. Or we can also say the slope at point P, or whichever point you're talking about. Okay, so how does this work? How can we find this? How can we generalize this for all curves? Because this is really what we want to do, is we want to get this to work in a way that we can find the slope of all curves. Well, we just plug in our values. So, I'm sorry, not all curves, all points on that curve of x squared. So let's plug in our actual function into this and see what happens. Okay, so we're going to take our limit. Whoops. We're going to take our limit as h approaches 0 for x plus h. Remember, we're talking about this function as our x squared function. So instead of f of x, we're going to use x squared, just like we have over here, right? Just like we have over here. So we're just replacing that. And then we have in our denominator, x plus h minus x. And this is going to give us our slope. All right, so let's work through this. Let's work through this slope of tangent line. So let's work through this. All right, so our limit as h is approaching 0. Well, let's expand this x plus h. All right, so we've got x squared plus 2xh plus h squared minus x squared all over x plus h minus x. All right, so you might notice that we've got a couple things that we can cancel out here. So our x squared and our x squared can cancel, and our x can cancel. All right, so let's keep on going. We have our limit as h approaches 0 is going to be 2xh plus h squared all over h. Now, if we just plug in 0 in here, we're going to get an undefined function. We're not going to be able to work this out. So let's see if we can continue to simplify this. So our limit as x approaches, I'm sorry, not as x, as h approaches 0 is going to be, well, let's factor out an h. I see that this is common in the numerator and the denominator. All right, so we can cancel out a couple of these, or we can cancel out these h's, and we are left with, what are we left with? The limit as h, I almost wrote x again, as h approaches 0, is 2x plus h. All right, so now if we plug in our 0, we're going to see that our limit is actually going to be like that. That's going to cancel out, and we're going to be left with 2x as our limit. So what does that mean? That means that this is, just like we said up above, this is the slope of our tangent line. So we could pick any point on our curve and we could find the slope at that point. So at the point 1, 1, we have a slope of 1, 1. We have a slope of, well, 2 times 1, so our slope is going to be 2. At the point 3, 9, so that was up on the curve. We could say, well, what is the slope at that one point, not all the way across between 1, 1 and 3, 9. What's the slope at the actual point 3, 9? Well, it's going to be 2 times 3, which is 6. Or you could pick any point. You could even say a negative value. What about at negative 2, 4? Well, that's going to be 2 times negative 2, and the slope will be negative 4. So this is a quick way that you can find the slopes of a tangent line, the slope of a tangent line, and a kind of a general way to find the slope of any given curve. And we're going to work on this a little bit more. So hopefully this helps give you an idea at least of how to find the slope at one specific point on a curve.